Today we are going to discuss in continuation with the lecture on propagation of electromagnetic wave in anisotropic dielectric medium, a very important law which is called Fresnel's law for phase velocity. Actually, we will derive a law, or you can say a result, in this lecture which is called Fresnel's law for phase velocity, and you will see that the solution of that result actually gives the idea of biaxial and uniaxial crystals. So this is its importance, and to start with the lecture on the phase velocity, or you can say Fresnel's law for phase velocity, we need the result which we have already discussed in the first part of this lecture. So I have just mentioned the two important results which we have discussed in the first part, and the first important result of the first lecture is d equal to 1 over mu naught omega square into k square e minus k dot e into k. You know here k is actually the wave vector, and this wave vector can be written as k equal to k into n hat. Here n hat is a unit vector in the direction of this propagation vector. So you can write this. Here will be kn hat and kn hat, so there will be k square term in second term also, and we will take the k square as a common factor. So d can be written as k square by mu naught omega square into e minus n hat dot e into n hat. Now you know that the phase velocity v is defined as omega by k, and in our expression there is k square by omega square, so that will be equal to 1 over v square, and hence the result for d may be written as d equal to 1 over mu naught v square into e minus n hat dot e into n hat. This is one of the important results of the previous lecture, and we will use it in the present lecture. And now the second important result which we have derived in the first lecture is mentioned here in heading 2. Actually, in case of the principal axis, we have seen that the x component of electric displacement is given as dx equal to epsilon naught epsilon rx ex, and from here you can find ex equal to dx over epsilon naught epsilon rx. You know the meaning of every term here. Actually, epsilon rx is what? This is actually dielectric constant in x direction of the anisotropic crystal, or you can say medium. And similarly, you can write Ey equal to dy over epsilon naught epsilon ry. Here epsilon ry is the dielectric constant in y direction, and Ez equal to dz over epsilon naught epsilon rz, and you know this epsilon rz is dielectric constant in z direction. So as the crystal is anisotropic, or the medium is anisotropic, so you know this dielectric constant will have different values in these three important directions x, y and z. And so epsilon rx, epsilon ry, epsilon rz are not same, but they are unequal. In case of isotropic dielectric, all these three quantities are same, and that is simply written as epsilon r. But in this case, epsilon rx, epsilon ry and epsilon rz are not same. Actually, these are the results which we have already discussed in first part of our lecture, and now in this lecture we will use these results, so I have mentioned it here. Now let us consider that the unit vector n hat, or you may say the propagation vector k, makes angle alpha, beta and gamma with x-axis, y-axis and z-axis respectively. Let us say this is n hat, and this n hat makes an angle alpha with x-axis, it makes an angle beta with y-axis and gamma with z-axis. Let us suppose it. In this condition, you can say that cos alpha, cos beta and cos gamma will be the direction cosines of unit vector n. So, let us consider cos alpha, cos beta and cos gamma are direction cosines of n hat. And if it is direction cosines of n hat, then we can express this n hat in terms of these direction cosines. You know this will be what? This will be cos alpha I plus cos beta j and plus cos gamma k. We can express this unit vector n hat in this manner. And let us substitute the value of the components of this unit vector n hat in equation A, which I have just mentioned above. Let us see, this is equation A, where actually the displacement vector has been defined. And now we will define the x, y and z components of this displacement vector D from equation A. And if you want to define the x component of D, what you will do? We will take x component of vector field E and also the x component of vector n hat. And so you can write the x component, y component and z component of displacement vector D from equation A using the components of n hat vector. So you can say in terms of components, equation A is given as. How we can write equation A in terms of components? You can see, if you want to write the x component dx, we will take the x component of the vectors in RHS. So this will be 1 over mu naught v square into x component of field vector E will be Ex minus n hat dot E. N hat dot E is already a scalar quantity, and here is n hat, and we will take the x component of n hat, and you can see the x component of n hat is what? This is simply cos alpha. So here will be cos alpha. Let us say this is equation A. And similarly, we will express the y and z component of displacement vector D. And for that you will take the y and z components in RHS of all of the vectors. So you can write dy equal to, what we will write dy? This will be 1 over mu naught into v square into EY minus n hat dot E into y component of n hat. And what is y component? This is cos beta. Cos beta. Say it is equation B. And similarly, the z component of the displacement vector, this will be 1 over mu naught into v square into Ez minus n hat dot E into cos gamma, because z component of n hat is cos gamma. And let us say this is equation 1. So we have just expressed the x, y and z components of displacement vector in this equation 1. Now we know for non-magnetic material, the refractive index is simply the square root of dielectric constant. So you know for non-magnetic medium or material, we know the refractive index, RF for refractive index, n is given as a square root of epsilon r, because mu r for it is equal to 1. We have already discussed it in previous lectures. But in case of anisotropic dielectric, this relative permittivity, or you can say the dielectric constant, has actually different values in different directions. And we have assumed that in x direction it is epsilon rx, in y direction it is epsilon ry, and in z direction it is epsilon rz. So the refractive index of this medium will be also different in x, y and z direction. And so you can write a refractive index of this medium, refractive index of this medium in x, y and z directions. If we write the refractive index of this medium in x direction by the symbol nx, we can write it, this will be a square root of epsilon rx. But the general definition of refractive index is what? We know, we define in general refractive index as the ratio of phase velocity of electromagnetic wave in free space divided by the phase velocity of EMW in that particular medium. And here we are considering only the x direction. So in general, nx is defined as c over vx. Actually here vx will be phase velocity of the EMW in x direction, and c, you know, this is phase velocity of EMW in free space. This is actually the general definition. And similarly, we can define the refractive index of the medium for y direction and for z direction. So let us write ny. This is refractive index in y direction. And what will be this? This will be simply a square root of epsilon ry. And from the general definition, we will write it equal to c over vy. And similarly, nz will be equal to root over epsilon rz, and this will be C over Vz. C over Vz. Again, we also know that speed of electromagnetic wave in free space is related to mu naught and epsilon naught. So you can write again, we know that C is simply equal to 1 over root over mu naught into epsilon naught. This is actually C. Now we will use these results which just I have defined in the equation B. I have just mentioned equation B here, which was actually the result of the first part of this lecture. This is equation B. You can see here I have defined Ex, Ey and Ez. And in this expression, there is epsilon Rx, epsilon Ry, epsilon Rz. And so actually we will substitute epsilon Rx, epsilon Ry, epsilon Rz in terms of the refractive index. So you can write from equation B after the use of these results in this form. So you can say, using these in equation B, what will be our result? You know, I am just repeating the same result. Ex is equal to what? We have seen that this is actually dx divided by epsilon naught epsilon Rx. And you can see epsilon Rx may be written as nx square. So we can write it as dx over epsilon naught into nx square. And again, from this definition, nx equal to C over Vx, we can write it as dx over epsilon naught into C square over Vx square. Let us simplify it to simplify it. This Vx square will be in the numerator now. So you can write this as Vx square into dx over epsilon naught into. Now let us see here. There is a factor 1 over C square. And 1 over C square will be what? You can see from here, 1 over C will be root over mu naught epsilon naught. So 1 over C square will be mu naught into epsilon naught. So this will be mu naught into epsilon naught. And you can see this epsilon naught will cancel out, and finally our result will be what? This will be actually mu naught into Vx square into dx. Mu naught Vx square into dx. So finally we can write the x component of electric field. Ex is equal to mu naught Vx square into dx. In similar manner, I am just writing the expression for Ey and Ez. We will change the subscript x to y and z, and we will get Ey and Ez. So you can say similarly Similarly, we can write expression for Ey and Ez. So what will be Ey? This will be mu naught into Vy square into dy. Say this is B, and in similar manner you can write Ez equal to mu naught into Vz square into dz, and this is C, and let this is equation 2. So we have defined the x, y and z components of the electric field vector in terms of the x, y and z component of the phase velocity, that is Vx, Vy and Vz. So here is actually Vx, Now let us use this equation 2a. See here, the value of Ex. We will use this value of Ex in equation, see here, 1a. You can see it here, 1a. What is 1a? This is dx equal to 1 over mu naught v square Ex minus n dot E cos alpha. In place of this Ex, we will actually write the expression which we have just obtained here. So let us use, you can say, equation 2a in equation 1a. So using 2a in 1a, what we will get after the use of this equation 2a in equation 1a, you can see we will write dx equal to what? This is 1 over mu naught into v square, and inside the square bracket the first term is Ex, and Ex you can see from here, this Ex is what? This is actually mu naught into Vx square into dx, and the second term is simply n hat dot E into cos alpha. Now we will simplify this equation to find the value of dx, and you can see if we take this first term containing dx in LHS, what will be the result? Let us take dx as a common factor. So here will be 1 and minus the first term in RHS has been taken in LHS. So this mu naught will cancel out, and simply our result will be Vx square over V square. Dx has been taken as a common factor, and in RHS what will left? This will be actually minus n dot E into cos alpha over mu naught into V square. And let us simplify this result. Take the LCM and simplify it. So you can see this will be dx into V square minus Vx square over V square, and this will be equal to what? This is minus n hat dot E into cos alpha over mu naught into V square. See here, this V square in LHS and in RHS will cancel out, and from this result you can write the expression for dx. So what will be this dx? You can see this will be actually equal to minus 1 over mu naught n dot e n hat dot e into cos alpha and over v square minus vx square. V square minus vx square. And equivalently, we may write this expression as 1 over mu naught into n hat dot e into cos alpha and over vx square minus v square. Actually, this minus sign has been multiplied in this term, and so here sign has been changed. So this is vx square minus v square. And in the similar manner, we can write the expression for dy and dz, seeing this result. So similarly, by induction, you can write expression for dy and dz. So what will be dy? You may write this is 1 over mu naught n hat dot e cos beta and divided by vy square minus v square. You can see we have just changed the subscript x by y and the direction cosine cos alpha by cos beta, because for y direction the direction cosine of n hat is cos beta. And similarly, you can write expression for dz too. So let us write the expression for dz. What will be dz? You can see this will be 1 over mu naught n hat dot e into cos gamma and divided by vz square minus v square. And this is equation 3. So we have just found the x, y and z components of electric displacement in terms of the phase velocity v and its components vx, vy and vz. Now we have already learned in the first part of this lecture that when an electromagnetic wave is propagated in an anisotropic dielectric medium, then actually the electric displacement vector d is normal to the propagation vector k. And so in this case, the scalar product of d and k or d or n hat will be 0. So as d is perpendicular to k, because you know in this case the electromagnetic wave is a transverse wave with respect to vector d and vector h, not with respect to vector e. K is not perpendicular to E, but K is perpendicular to D. We have already discussed in first part of this lecture. And since this K is in the direction of n hat, so you can also say that this vector D is perpendicular to n hat, because n hat is a unit vector in the direction of propagation vector k. And since D is perpendicular to n hat, so this implies that this dot product D dot n hat is equal to 0, because you know the scalar product of two mutually perpendicular vectors is always 0. And we can write expression for this D dot n hat in terms of actually their components. So you can write, if we will write this D as dxi plus dyj plus dzk and n, so you may simplify it. This is dxi plus dyj plus dzk, and dot n hat, you know, this is cos alpha I plus cos beta j plus cos gamma k, and this will be equal to 0. Now let us take the scalar product. You know, in case of a scalar product, only the corresponding terms remain on 0, and all other the cross terms become 0. So this will be simply dx cos alpha plus dy cos beta plus dz cos gamma, and this equal to 0. So say this is equation 4. Now you have already found in equation 3 the x, y and z components of electric displacement D, that is dx, dy and dz have been found already in equation 3. And now let us put the values of dx, dy and dz from equation 3 in this equation 4. You can see here we will substitute for dx, here for dy and here for dz from equation 3. So after the use of equation 3 in equation 4, what we will get? So putting for dx, dy and dz from equation 3 in 4, what we will get? You can see actually when we will substitute the value of dx, dy and dz, you can see that in all terms n dot e over mu naught will be a constant factor, will be a common factor, not constant factor, sorry, but a common factor. So let us write by taking this as a common factor. So you can write it as n hat dot e over mu naught. This will be a common factor of each term. So I have taken it as a common factor. And what will be the remaining term? You can see the remaining term actually contains, in first term contains cos alpha, and here there is also cos alpha. So this will be simply cos square alpha over Vx square minus V square plus cos square beta over Vy square minus V square plus cos square gamma over Vz square minus V square, and this is equal to 0. So we can simplify this result in this manner. This will be simply cos square alpha by Vx square minus V square plus cos square beta over Vy square minus V square plus cos square gamma over Vz square minus V square, and this will be equal to 0. This is our final result, and this result is actually known as Fresnel's law for phase velocity of the electromagnetic wave traveling in an anisotropic dielectric medium. So this result is Fresnel's law for phase velocity. Actually, you can see this equation indicates that the phase velocity V in general can have two values in any given direction, because it is quadratic in V, so V will have two values in any given direction. However, for most anisotropic media, it is found that there are two directions for which this equation C has only one solution. And when you say this equation has only one solution, what does it mean? It means it gives only one phase velocity in case of most of the anisotropic dielectric. Actually, these directions for which V has only one value are known as optic axes. In polarization topic of optics, we actually study it in very detail, and so this direction is known as optic axis. And the material for which this V has only one value in two directions is actually known as biaxial crystals. Although, as a special case, there are also uniaxial crystals in which there is only one optic axis. And here you should remember that optic axis is a direction in the medium or crystal. It is not a line. It only determines, it only indicates a direction. So I have told you this result obtained in equation C is the Fresnel law for phase velocity V, and this was our purpose, our aim of this lecture, to find this phase velocity, and what conclusion we draw from it, I have just mentioned it. So I am just now writing the important facts contained in this relation. So you can say this equation C is Fresnel law of phase velocity. The another important conclusion is what? You can see that in accordance with this equation, phase velocity V has two values in a given direction in general. So V has in general two values in a given direction, in a given direction. But as I have told you that it is also found in case of most of the anisotropic dielectric that there are two directions for which V has only one value. Phase velocity has only one value. So if V is unique for two directions, then the crystal is called biaxial. But as I have told you, in this case actually there are two optic axes, and but there may be some crystal for which there is only one optic axis, that is called uniaxial crystal. Uniaxial crystal. So this is all about the propagation of electromagnetic wave in an isotropic dielectric medium. We have completed this lecture in two parts, and so in continuation you should follow or you should watch both of the videos in continuation. Then you will understand the facts which I have already discussed in these two lectures. Actually, my writing pen has been destroyed, and this lecture I have just recorded with my finger. So you can see the handwriting is very bad, but due to this, in the two coming days, my lecture will not come on YouTube, and after 2 days I will get again my writing pen. Sorry for inconvenience, for bad handwriting you can say, and when my pen will be again with me, then again I will clearly write all the lectures for you.